Hello everyone, welcome back. This is lesson 35 for Calc AB, where we are learning differential equations. And in this video right here, we're going to talk about some applications to differential equations. And one of the biggest ones is something called exponential growth. And in order to just do the type of questions that we need to do, we need to first of all take this differential equation and rewrite it into a function that we can use with exponential growth. Now, you guys remember exponential functions has an e in it, right? An e to it. So what this question is saying is the derivative is equal to a quantity, whatever this quantity k is, that's directly proportional to our y. And you guys learned that back in Algebra 1, Algebra 2, where we talk about, directly proportional and indirectly proportional functions. Well, this derivative is directly proportionate to some value of y. So let's solve this differential equation and get us an actual exponential growth function. So when I do this, k is constant. I'm going to go ahead and separate my variables, which is what we're going to end up doing. And I'm going to do dy. I'm going to move the y on the bottom. And then I'm going to leave the constant alone. Yeah, the k could have went with the y, but why add a fraction if you don't need to? Right? Let's leave the k in the numerator. And so I'm going to go ahead and do this. So dy over y equals k dx. And just like in previous videos, we are going to integrate both sides, which is pretty easy to do. We know that this is going to be the natural log, right? It's 1 over y to the first power. So we know this is going to end up being the natural log of absolute value of y. And this constant k, when we integrate some constant k, it just be some constant kx, and then plus a c. And what we now understand is how we get rid of y. Well, how do we get rid of y when we have the natural log of y? Well, how do we isolate y? How do we isolate y if we have the natural log of y? Well, again, you guys learned back in good old pre-calculus that you could raise everything to the e power, because if e to the a is equal to e to the b, then a and b have to be equal to each other, so we haven't changed the problem. So we can do this. Well, another property that you guys learned back in good old pre-calculus is that e to the natural log of anything is that thing. So I can now say that the left-hand side is going to be just the absolute value of y. And so I'm left with e to the kx plus c. So we're almost done now with what we have to do here. We can drop the absolute value. All right, we can drop the absolute value of our function because e to anything is always positive. And then the other thing we can do here is our exponent rules is we can say e to the kt, e to the x to the kx. I'm getting used to what we're going to do later. E to the kx, and then we can rewrite this as e to the c, because again, with our power of exponents. So e to the a times e to the b is actually e to the a plus b. And so what I want to show you guys here in this particular example is that this is still a constant, right? E raised to the c power is a constant. It's a constant. So we're going to call this constant a. Okay? We're going to call this constant big old capital A. And so what we can now do is rewrite this as y is equal to a e to the kx. All right, and this is going to be our differential equation that now takes what we have here, and now we have an actual equation for it. The other thing I'm going to tell you guys is just as a side note that you guys may be able to use as we move along here, is y is equal to a e to the rt. And these are the same thing. All right, so this has to do with x. Our constants are constant. This is in time. So k, r, they're the same thing. This could have been completely an r. So this is the rate. So k is a rate here. And then this is going to talk about our value, right? So this is the other way to write this up. I'm going to use this one more than this one, but they're the exact same thing. All right, so let's go on and look at an example. Before I do that example, we can see here that dy over dt is equal to kx. So we started with this, and this is translated to, again, y equals a e to the kt. Notice that they've already changed the x to the t in this example. And again, any of these variables really, as long as you guys understand what these represent, as we go through some examples, you will understand them all. They're all interchangeable with each other. They're all interchangeable with each other. All right, so let's go to a classic question for exponential decay or growth and decay. So this is going to be a growth problem. Is a bacteria problem. So it says bacteria in a lab culture grows in such a way that the instantaneous rate of change of bacteria. All right, let's look at that for a second. So instantaneous rate of change of bacteria. So that's going to be our derivative, right? Instantaneous rate of change, we can immediately say that that is going to be a derivative. So instantaneous rate of change is a derivative, but it's a change of bacteria. So we can say that the change of bacteria, so I'm going to call B our bacteria. So let's go ahead and write that as our thing. So B is our bacteria. Or actually, it's our quantity. It's how much bacteria with respect to time is equal to directly proportional. So we have some constant, K, directly proportional to the number of bacteria present. And we've already agreed that bacteria is B. Now, this is where you do not have to go and do this solving the differential equation again. And it says solve it, so yes, we technically would. But I want you guys to know that, going back up here, these letters are interchangeable with each other. So you can see that these are Y's here. Well, these are B's here. So I can immediately jump to the fact that Y is going to be equal to some constant A, E to the K, T. All right. And again, R, K doesn't really matter. Right now, we're just going to say it with the K. So this solution is going to be A, E to the K, T because of what I did at the top. It's right there. So you guys can automatically jump to this. All right, jump to that. The other thing that I want to say, just as I'm writing this out, is maybe write this as Y to the T. So it's a function in terms of T. And I'm going to show you guys that while we now do the problem. So that just gets to that. So it says, suppose that there are 3 million bacteria present initially. So what does that mean? That means that at time equals 0, there are 3 million bacteria. Now, I'm going to go ahead and just say that B is going to be represented in bacteria per million, because I'd rather deal with a 3 than a 3 million. So if I say now that bacteria, and so this is one of the things that you guys should write out in your problems is, what does this variable represent? And if it's in millions, then I can just say that B is equal to 3. And it says after 3 hours, so when time is equal to 3, my bacteria has doubled. So now my bacteria is at 6 million. And so it says, write the differential equation that describes this relationship, which we have, which is here. And then this is actually the same thing. This does represent the relationship. It's not a differential equation, but it is. And it says solve the differential equation. So we want to know what all these values are. So that's what this actually means. Solve the differential equation. What is the A and what is the K, right? So what is the A and the K is what we want to solve for. And we have enough information to actually solve that right here. So the first thing we're going to do is we're going to plug in, when we have Y equals 0, we get A, E to the K times 0. Well, this is just 1, right? Because 0 times K is 0, and so E to the 0 is 1. So we get that, and we actually know what that value is, right? We know that the Y of 0 is actually equal to 3. So 3 is going to be equal to A times 1. So our A, which is going to be equal to 3. Now we can say one more special thing about this example. This is always going to be your initial value. Always. It's how much you have at time equals 0. Because when you plug in 0 for time, this will always be 1. So again, ladies and gentlemen, you actually know if they give you an initial value, what that is. You can automatically plug that in here. So I'm going to go ahead and write my function out again and just replace 3 with A. And so we have a 3 now done. And again, the only thing we need to solve for is K. Well, I've got another solution here. I got another little piece of our puzzle that we can work on. So when time equals 3, so y of 3 is equal to 6. So I can say 6 is equal to 3ek, and then time is 3. So now I can solve for k. Well, I can divide by 3, and I'm going to get 2 is equal to e to the 3k. I can now, in order to get this down, we can add the natural log. We can add the natural log to both sides. Right? And so then the natural log of e raised to anything is just going to simply be that exponent. And so k is going to be equal to 1/3 the natural log of 2. 1/3 the natural log of 2. And I'm going to go ahead and just write it down here. So it says solve this equation. So we actually can now say what this is. We can actually write down what the equation is. So y of t is equal to 3e to the 1/3 natural log of 2 times t. Okay? And so we have now solved this differential equation. And again, I hope that makes sense. You guys, again, can always jump to this. You got to find the a. Do they always give you the initial condition? No. So those some examples we're going to do. We're not given that. But if we are, then absolutely plug it right in. And then you can use, some other information to find these other values. And then the second part of this problem is simply asking us to look at, what will the bacteria of the population be 1 full day after the first measurement. So this question is simply asking us, what is the bacteria? So what is our bacteria when our time is equal to 24? So y of 24 would be equal to 3e to the 1/3 natural log of 2 times 24. And remember, this answer is in millions, right? This answer is in millions. And I will tell you guys that this is definitely a calculator question. And when you solve for it, we get 768, which we all know now is in terms now of millions. So we are actually going to get 768 million bacteria, which is kind of crazy if you think about it, that it initially started with, 3 million bacteria. And then in the third hour, we're at 6 million. And so it really, you guys can see this exponential curve that it really goes up, as time goes on, it's really going up really high. So that's it for this video. I hope this was helpful. We're going to come back in the next video and talk about more application problems for this. And I'll see you guys then.